factor now. So bringing it all together a little bit, hear me out. So what if we wanted to remove the impact of irregular fluctuations, or if we wanted to remove the impact of seasonality to try and see, is there actually an underlying pattern that's being obscured by these things? And we can. So that's actually how we link in smoothing and deseasonalizing data. So again, I'm trying to help you make these connections. So when we're talking about irregular fluctuations, we're talking about kind of those random ups and downs that might kind of obscure the underlying relationship. And so it can actually make what's actually going on really hard to see, because it's kind of like obscuring it. It looks really messy up and down. But if we apply smoothing, we can actually remove the effects of that and kind of look for those underlying patterns and trends. And then same, if we have seasonality present in our data, by deseasonalizing it, we can actually remove the impact of seasonality so that we can see if we put the impact of seasonality aside, do we actually have any trends or patterns there. So smoothing, we have the 3 moving average and the 5 moving average, also kind of referred to as the 3 moving mean or the 5 moving mean. Probably familiar with those terms. And we can also do the 2 moving mean and the 4 moving mean, but when we do it that way, we need it with centering, which we won't be going into it either today for the sake of time. So again, the idea behind our 3 and our 5 moving mean, the name comes from how many points we're taking the average from. So with the 3 moving average or the 3 moving mean, it's 3 because we're taking the average of 3 separate points to get the average value for our starting point, and then we do that all the way through our data. So that we kind of get that effect of because we're taking all these averages, we're kind of in effect we're smoothing out the data. Think about it like we're ironing out the irregular fluctuations. We're removing them. We're trying to get rid of them. So we actually can't take the 3 mean smoothed value for January, because if we were going to do it for January, we'd need to take the point for January, the point before, and the point after. But we don't have a point before January, so we actually can't do January. So January is off the table. But we can do February by taking the value for February, the value for January, and the value for March, adding them together, 12, 8, 7, which gives us 27, which we divide it by 3, because that's a number of, the number of values that we've taken, and that gives us 9. So our 3 mean smoothed value for February is 9. And then we can find the value for March by getting the average of February, the average of March and April, adding them together, 8, 7, and 14, add them together, divide them by 3, just like with any other average, and we get 9.67. We can do the exact same all the way through. And we can also do the exact same with the 5 moving average. The main difference being that we actually lose our first 2 data points when we do a 5 moving average. And that's because again, we don't have 2 points before January to use. We don't have 2 points before February to use. But when we're looking at March, we can take March. We can take the 2 points before and the 2 points after, divide them by 5, add it all together, and then we can actually get the smoothed value for March. And once we've done all of our smoothing, it can be a bit of a time-consuming process, and that's why it's usually kind of handy, kind of convenient and nice and neat to kind of do it in a table or whatever kind of format works best for you. But once we have all of our values, we can actually plot our smoothed value on our time series plot as well. And that's actually super helpful because it actually makes it really, really clear if there is a trend or a pattern or a relationship that it has uncovered. And we've got a key here. So we can see that this here is our original data, and you can definitely start to see what I'm meaning by irregular fluctuations. We've got all these crazy ups and downs. I actually can't really see if there's a pattern or a trend there because it's just so up and down and obscured by these annoying irregular fluctuations. So what we've done is we have applied smoothing, and you can see here we've got our 3-point and our 5-point. But because it's actually in black and white, it's kind of hard to tell which is which. They look quite similar. We've got our circle and our square. But another way that you can kind of tell the difference between them is by looking at how many points there is. Remember what I said before about how when we do the 3 moving mean, we actually lose the first point, which here is January, and the last point, which is December. So I can actually really easily tell, even without looking at my mean, that this must be my 3 moving mean smoothed data, because I've lost my first and my last point, which means that this line here must be my 5 moving mean, because I've lost my first 2 points and my last 2 points. So that's kind of the difference there. So we can start to, and as we look across at the different kind of lines, we can actually really clearly see the impact that our smoothing is having. You can actually kind of see that ironing out effect, that smoothing down. We're kind of ironing out the irregular fluctuations, because we can see our 3-point mean smoothed line here. We can actually see that a lot of these crazy high irregular fluctuations have kind of really been, like we've said, been ironed out by taking those averages. And our 5-point line has been even further smoothed. Those really big variations have been even further ironed out. And if we have a really close look, we can actually start to see that maybe there almost is a bit of an underlying trend there. Because if we were to fit a trend line to our 5-point smoothed data, we actually might even start to see that maybe there is a little bit of an increasing trend there. Because now that we've got the effects of our irregular fluctuations moved out of the way, we can kind of start to see that a little bit more. So that's really interesting there. Again, we won't be touching on that. So that was removing the impact of irregular fluctuations. But if we want to remove the impact of seasonality, this is where deseasonalizing data comes in. And how we do that is with seasonal indices. So we won't focus on here too much, because I would like to focus more on sequences. But the main things I'll draw your attention to is, again, that a season is any breakdown of time with equal periods in the year. So again, if we could do it month by month, in which case we'd have 12 seasons in the year. And seasonal indices, which are like the numbers that we use to deseasonalize and reseasonalize data. So these seasonal indices, what they're doing is they scale information to reveal trends without the influence of seasons. So if, for example, I had a time series plot where I plotted ice cream sales throughout the year, you'd definitely expect there to be a big spike in the summer months, and then in the cooler months, I probably wouldn't be selling so many ice creams. So if I wanted to know, is my business doing well because it's summer, or is my business doing well if we removed the impact of temperature from our data, that is where like deseasonalizing would come in. So that is, again, it's just removing the impact of seasonality. So yeah, like I said, we can see, is our business doing well because it's summer, or is our business doing well in spite of the fact that it's summer? So again, removing that impact of seasonality. And again, it makes our data more readable. So a seasonal index is usually a number around 1, because seasonal indexes are based around that average point being 1. And the sum of your seasonal indices will always equal the number of seasons. So if we're looking at days in a week, we'll have a seasonal index for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And the sum of all those numbers will add up to 7. And any of the points, any of the seasonal indexes that are below 0 means that it's a below average day, and anything below 1 is below average, and above 1 is above average. So for example, a seasonal index of 1.3 means that that season is 30% above average. So if I said, for example, if we were doing like ice cream sales throughout the year, and if the seasonal index for summer was 1.3, that'd mean the seasonal index, that means ice cream sales in summer is 30% above average. So that's really important to keep in mind, that when we're interpreting seasonal indices, we're always coming back to what actually is the average. That's what we're coming back to. This is our formula to calculate the seasonal indices. So the seasonal index, so that number, that'll probably be around 1, a bit below, a bit above 1. Our seasonal index is equal to the value of the season. So for example, the number of ice creams sold in summer divided by the seasonal average. So that's, again, the seasonal average. You've got to calculate that before you can find your seasonal index. Again, A quick reminder that if you add your seasonal indices together, it will equal the number of seasons. So that can be helpful if you've got to find an unknown seasonal average as well. And again, if it's 0.87, that means that it's 13% below average. We're always coming back to the average. Like with any formula, it can be rearranged. So if we have our deseasonalized value, but we want to re-seasonalize the data to get back to the actual value, again, we can rearrange our formulas to do so.